So next problem also it has now it has at least the states are four states which we see, right? And so that means you see that it is a counter which is going from 00 to 01, right? Then it is going to from 01 to it is going to 10, 10 to it is going to 11, and then 11 coming back to 00, right? That is what the state machine is, right? Okay, so now when this is the kind of state machine, or in this case it is a counter, 2-bit counter which we are implementing. So we see that there are 2 bits we need, right? And 2 bits means that we are needing 2 flip-flops, right? So 2 DFFs which are needed. So that means if we write a state transition, we have to write first. There's no external input, right? No external input. External. So when I say external input is what I mean by uh, that an input on top of the present states, right? Because that is, if the present state are the only one, so let's say these are my present states, um, which are Q. Uh, so this is a T, right? That is my present state. But there is no external input which other than this, right? Which is defining. So that means there are only 2 inputs. And when there are 2 inputs, we can just describe it as 0, 1, 1, 0, 1, 1. These are the possible inputs. Now the next state we know Qt plus 1 and Q0t plus 1. We know this is going to be just the next one. So when it is in 0, 0, we know it wants to be in 0, 1. When it is 0, 1, this wants to be 1, 0. This is 1, 1. And this wants to be, when it is in 1, 1, it wants to be 0, 0, right? So that is what we have seen. And so this is what we have drawn. This is your state table, right? So you have converted this problem into a state table. Now that is where you can start from, and then you see now only thing you have to add is 2 columns for what should be the D input, right? So D1 and D0, which is now you have to look at in the excitation table. So it's very easy in a sense. D is just copying the Q1, T plus 1, so that would be 0, 1, 1, 0, right? That should be the D input if you want next state to be that, and D0 should be 1, 0, 1, 0, right? That is your step. So with that is one can also write, now I have to write D1 as a function of 2 inputs, which are Q1 and Q0, right? These 2 inputs, these are inputs, right? And yeah. So then you see that if these are the 2 inputs you have to write, D1 and D0, you can clearly see from the table, or you can do the Carnot map. Carnot map, if you do, let's say D1, you are representing in terms of Q0 and Q1, right? Then you will see that the entry which you get is the diagonal entries, right? Which gives you that these one is the XOR of this Q and Q0. Similarly, you can do for D0. D0 is D0, where are the entries? So this is the first entry, and 0, and then this entry, right? So then we see this is the first column of the Q bar column. So D0 becomes Q0 bar, right? So with that, then you can implement this also using 2 flip-flops, which you have seen. So there is this flip-flop which is coming. Now we can represent this as a T1, Q1, Q1 bar. This is your D0, Q0, Q0 bar. This is the D flip-flop. Clocks are connected together, right, to a clock signal. It's the heartbeat of your circuit. Now the main thing is how the inputs are connected. You see D0 is just Q0 bar, so then we can just connect it to Q0 bar. But the other input is the Q1 plus Q2. So there is a XOR gate which we have to make. And in this gate, there is one input which is coming from here, right? and there is another input which comes from this part, right? That's the Q, right? So when you make this circuit, you see now only input, it does not have any other external input. In a sense, only clock is one of the input, and then by itself, it is going into the whatever state, or it is counting the way we are counting this thing, right? So that is what is happening in this particular circuit. Okay, so that is what is the way to implement this state diagram, which you have seen here, right? And then we can go to the next one, which is more involved problem, right? So it has two parts. Let's do both parts. So I can continue maybe as the part one here, and the part two I can do separately. Okay. So part one, if you see in this problem, it is saying first thing would be again to convert this problem into a state diagram, like what we did earlier, right? So their state diagram was given that it's a counter, but here we have to convert it to the state diagram. So state diagram means that you know that there are, first of all, in this particular thing, it is saying there are two states which are there, right? So that is the one thing to figure out. Okay, there are two states. One is S0 where the Q is 0, right? So this is 0th state. And one state is S1 where Q is 1, right? So that means if there are two states, we know that only one flip-flop is there, right? One defect needed, right? So one DFF needed is that we know that only one input is coming from the DFF, which is the Q naught, right? Now let's write the other problem. What is that the only input Q naught? No, there's another input which is X, and X is what it is saying is X is defining if the 10 rupee coin is inserted or not, right? That is what it is. The X is the external input, external input. Yeah, that is a 10 rupee coin. So that is so that means if we see there is a 10 rupee coin inserted or X is 1, then we know that this is going to go into the state, right? But what is the output? Is it the same? There is a output also Y, which is the action output, right? Y means Y equal to 1 is when uh, chai is poured, right? So that is the output which comes from there. So when we see that this X is 1, in this case, there is Y is basically 0, right? Because you go, when you put a 10 rupee coin, it is saying that you go only from state 0 to 1, right? But chai is not poured yet. Chai is poured when you go from, you are in state 1 already, and you put a X equal to 1, that means 110 rupee is put. Then the 20 and rupees are there, and then this posts the chai to 1, right? So when X and Y are 1. The other two states of X are, which you see are when X is 0, we see Y is 0, right? Nothing is happening. Similar to this is when X is 0 here, right? In the state, Y is 0. Nothing is happening, right? So that is the your state diagram, which you see, which we have drawn, right? And we have labeled, you can make it more beautiful. Just that, yeah, I mean, I was not very, but you can make it more beautiful and clean, right? This is this and this, so it's just a transition to this, right? So then one can now go on and look at, okay, what do I need to do? I need to now find the state table. That is what are my inputs to this? And I know that there is one external input which I have X, and I have only one state in this. One state means one bit. That means I'm only using one flip flop. So that means there is only one present state which is needed, which is Q0, right? And the next state I know is decided by these two things, right? So let's write all the combinations of these inputs: 0, 0, 0, 1, 1, 0, 1, 1. So when I'm in zero state, let's now look at from the state diagram and populate. When I'm in zero state and input is zero, where do I remain? In zero itself. When I'm in one, state is zero, I remain in one. When this is in zero, right? I'm in zero and the coin comes, I go to the state one. When I'm in one and the coin comes, right? X is one, then where do I go? I go to state zero. And similarly, you can draw for y. Y would be, you see that accordingly you can look at this and you can draw, right? Only when 1 is there and you are in state 1, right? Or x is 1, then only y becomes 1, right? So this is the state table. You can see that state table is basically this part one can make. Now, once you have made a state table, the next would be obviously to make a D uh, input or excitation table. So that means based on these two states, right, you are going to make a excitation table. And in the excitation table, we see you have to just copy qt plus 1, right? Q naught 2 plus 1, that is your d naught. So now once we have d naught, we can write d naught, solve this in terms of your q1 and x and q naught, right? So x and your q naught, and this is your for d naught we are solving, and then you see it is a yeah, it's a XOR function, right? That is what it is. So d naught is basically q naught plus XOR x. Similarly, one can calculate for y, because y is the actionable output, which is pouring the chai. Is we see this is also in terms of these two truth table. One can see that it is. Let me just draw. Right. So you can see that for the case, so this is your Q naught, this is your X, right? So, sorry, yeah, this is the Q naught and this is X. So for this three cases, we see this is Y is 0. For only Y 1, 1, this is 1, which is, that's why our Y becomes just the end of this D naught. So what other inputs are your Q naught into X? Okay. So then one can implement the circuit using one D flip-flop. Q, this is D naught, this is Q naught bar, this is the clock which we are feeding in. And now we see if I have to implement, there is an external input which was there X, but the X is also XORed with Q naught, then this goes into D naught. This is what, and then there is an external for actionable. This is a separate circuit which can be, so this gives you one. So that is what is the gate level circuit of this particular problem you will see. Okay, so now we'll move to the next part, which is more involved. That means there are more inputs, and we'll be able to see how we go through that problem.